All right, welcome back. Let's move on to our review of Chapter 2. All right. Chapter 2. So this is the chapter that deals with the notion, the most important notion here by far is the notion of the supremum slash infimum of a non-empty set of real numbers, which is bounded above, and the so-called completeness property for R, which says that any non-empty subset of the real numbers, which is bounded above, has a supremum. Okay, but the first section is entitled Algebraic and Order properties of R. Okay, and this section is at once important and unimportant. So what happens in this section is that in the real numbers, we identify some basic axioms, the basic axioms that govern the way that addition works, that multiplication works, and the way that they interact. So things like the commutative rule, associativity, the existence of an identity element, right? The idea that a plus 0 is equal to a, and a times 1 is equal to a. And the notion of distribution, which tells you how multiplication and addition interact. And from those basic axioms, section 2.1 goes on to develop the notion of order on the real numbers and basically develop all of the algebraic and order theoretic manipulations that are kind of second nature to you, should already be second nature to you. So, somehow you have to know everything from this section, but probably you pretty much already do know everything from this section. And basically, the most important thing is being able to manipulate and solve inequalities, okay? And I'm not asking you to be able to prove anything from this section, so I don't want you to study how to, say, establish that 1 plus minus 1 is equal to 0 or something like that. Okay, so I guess the easiest way to say that is no, but no proofs. Okay, so the material you should already know innately, basically, and I'm not going to ask you to prove anything from that section. So that covers section 2.1. All right, section 2.2 is the section on absolute value, which is, of course, very important in this course. Okay, so we have the definition. The absolute value of a real number a is equal to a if a is greater or equal to 0, and minus a if a happens to be less than 0. Okay? And then we have an oft-used fact, the triangle inequality, which has two main formulations. The first is that the absolute value of a plus b is always less than or equal to the absolute value of a plus the absolute value of b. And the second sort of goes the other way, and it tells you that the absolute value of a minus b is always greater than or equal to the absolute value of the difference between the absolute values of A and B. Okay, so one inequality involves A plus B, the other involves A minus B. One gives you a less than or equal to situation, the other a greater than or equal to situation. You should know both of those facts about the triangle inequality. And then the only other thing of import from section 2.2 is a piece of notation which gets used fairly frequently in the text, maybe a little less so in class. And that's the notion of an epsilon neighborhood. So if epsilon greater than 0 and x is a real number, the epsilon neighborhood of x is the set. So it's usually denoted by v sub epsilon of x. And that's equal to the set of all real numbers y with the property that their distance from x as measured by the absolute value of y minus x is strictly less than epsilon. Okay? So there's the epsilon neighborhood of a point on the real line. Okay? And that concludes the stuff that you really need to know from section 2.2. All right, so pause if necessary to write down. Again, I'm going to post the notes, so if you want to just follow along, that's fine. Okay, this is an important section, section 2.3. This is on the so-called completeness property. Of R. And it really is important because it's what makes R, right? It's what really differentiates it from, say, the natural numbers or the integers or the rational numbers, okay? It's this idea that you do have the notion of a least upper bound that just does not exist for, say, rational numbers. So first we'll start with the definition. So S will just be some general subset of the reals. So part 1 is that S is bounded above if there exists alpha, alpha in the reals, such that x is less equal to alpha for all x in the set S. Okay, so there's some upper bound for S. Bounded above. And of course we have the similar notion for bounded below. So 2, S is bounded below if there exists alpha in the reals such that alpha is less equal to x for all x in S. Okay? And 3, finally, S is bounded if it is bounded above and below. Okay? And I guess maybe it's worth mentioning that sort of quantify this quickly as follows. Say, i.e., there exists some, I don't know, m greater than 0 such that the absolute value of x is less equal to m for all x in S. That's another way to put it. Oh. Okay. So that's bounded above, bounded below, and bounded. Now we can define the all-important notion of the supremum. So, definition. If S is not empty and bounded above, then a number alpha is the supremum of S if two things are true. One, alpha is an upper bound, so alpha is greater or equal to x for all x in S. And two, if you have some other number v greater or equal to x for all. Hello, Aaron. How you doing? I see. Well, we're recording a lecture here. You want to say hi?
Hello.
All right, that's Aaron. He's 10. We're going to go on a walk in a little bit, okay? But I got to finish this review. All right. Okay. So if v is greater than or equal to x for all x in S, then alpha is less equal to v. Said another way, if v is any other upper bound for S, then alpha is smaller than v. So alpha is the least upper bound. Okay? So that's the definition of the supremum. And then, of course, we have, see how much of this we can recycle. Okay, so for the infimum, you want a non-empty set which is bounded instead below. And then alpha will be equal to the infimum of S if alpha is a lower bound, so alpha is less than or equal to x for all x in S. And if v is also a lower bound, that is, v is less than or equal to x for all x in S, then alpha is now greater or equal to v. Alpha is the biggest lower bound, the greatest lower bound for this non-empty set S, which is bounded below. That's the definition of the infimum. Okay? So we have the sup. We have the inf. Okay? And then I guess I should say since we're here, let's talk about, there's also an alternative to part 2 here, which can be useful. Okay, so we'll start with the infimum and go back to the supremum. So it is also true that a non-empty set which is bounded below has alpha, the infimum of S, if, first of all, of course, alpha is a lower bound for S, and then secondly, we can replace part 2 here with a different condition. If epsilon greater than 0, then there exists an x sub epsilon in S such that x sub epsilon is less than alpha plus epsilon. In other words, if alpha is the infimum and you make it just a tiny bit bigger, then you can always find something from the original set that's smaller than that. Okay? So somehow no amount of perturbation, no amount of making alpha a little bit bigger is allowable. That's what makes alpha the greatest lower bound. Okay, so that part 2 is the alternative definition for the infimum. Okay, and then we can also do something similar for the supremum. So we'll have to change this stuff again a bit, right? So if S is now non-empty and bounded above, then alpha once again is the sup of S if alpha is greater or equal to x for all x in S. Right, so it's a non-empty, bounded above set, and alpha is the sup if it's an upper bound, and if epsilon is greater than 0, then once again there exists an x epsilon in S such that x epsilon is greater than alpha minus epsilon. Okay, so the idea here being that alpha is supposed to be the sup, the smallest upper bound. So if you make alpha smaller by any amount, no matter how tiny, you'll always be able to find something from the set that's bigger than that now slightly smaller number. Okay, so alpha is the absolute smallest upper bound that you can possibly get. So that's the second definition. All right. So that's the definition of the sup and of the inf, 2 different ways each. And that brings us to the completeness property. The completeness property of R. And all this says is that every non-empty set in the reals which is bounded above has a supremum. That is a statement you should absolutely know for the exam. Completeness property of R. Okay, so then section 4 really only has a couple of things we need to cover. These are applications, direct applications of the completeness property for R. Okay, so section 2.4, applications. So the first one is the so-called Archimedean property.
which we have typically abbreviated by AP, not to be confused with the Associated Press. If x is any real number, then there exists a natural number x such that nx is greater or equal to x. No matter how big a real number you have, there's always a natural number bigger than it. Which again seems like, I think we had a discussion about this, and this seems utterly unremarkable, even asinine to remark on, but it means something, and the reason it means something is because what we're sweeping under the rug is that building the real numbers all the way from the naturals to the integers to the rationals, and then the big jump to the real numbers, through that whole procedure, things get pretty complicated and pretty messy. And what this Archimedean property is saying is basically that in that process, you preserved sort of the natural connections between these objects, right? That after all that incredibly hard, messy work to build the real numbers, the natural numbers fit exactly where they're supposed to in the real numbers, okay? So it's good to know that you didn't screw something up along the way. The other consequence I want to mention from this section is the so-called density theorem, which has a pretty simple statement as well. Density, right? It says if x is less than y in R, then there exists, say, a rational number and an irrational number, so that would be an R without Q, such that both this rational number and this irrational number fit in between, strictly in between x and y. So between any two distinct real numbers, you can squeeze a rational and you can squeeze an irrational. In fact, you can squeeze as many as you want within reason. For the rationals, you can only squeeze countably many in there because there are only countably many rationals. For the irrationals, you can squeeze uncountably many irrationals in between x and y. But in both cases, there are an infinite number of numbers, either rational or irrational, between x and y. Okay. And then that brings us to the most important application here in this chapter. So section 2.5, and section 2.5 contains the nested intervals property, or the nested intervals theorem, which I will summarize as follows. Okay, so 2.5, nested intervals. So here's the theorem. If I sub n is a closed bounded interval for each n, and if these intervals are nested, meaning that I sub n plus 1 is contained in in, or n in n, then the intersection from n equals 1 to infinity of all of these intervals is not the empty set. Okay? There has to be something in there. There is something that belongs to every single one of those intervals. All right? Right. Now, at various points in this course, and possibly at various points in the exam, it will be helpful to know something a little more detailed about exactly what this intersection looks like. So let me go a little further and say something about that. So you say, in fact, the intersection from n equals 1 to infinity of these I sub n's is itself a closed and bounded interval whose left-hand endpoint is the supremum of all the ANs, and whose right-hand endpoint is the infimum of all of the BNs. Okay? Because the fact that these intervals are nested means that these ANs are an increasing sequence and the BNs are a decreasing sequence. And as we saw in the proof of the nested intervals property, any one of the BNs turns out to be an upper bound for all the ANs, and any one of the ANs is lower bound for all the BNs. So this infant soup definitely exists. All right. So in fact, this is the case. And finally, if the length of these intervals is going to 0, then the length of these intervals is going to 0, then of course the intersection from n equals 1 to infinity of the INs is equal to just a single point. Okay, and that has happened a few times and has been useful to us a few times, most recently when we were talking about the location of roots theorem. Okay, and then finally, although we won't need to know the proof for this final exam, just the fact, as a corollary, one uses this directly to prove, this is one of many different ways to prove that R is uncountable. Okay, and that takes you to the end of chapter 2. All right, and I will be back hopefully tomorrow with chapter 3. All right, bye.